Swayam Prabha. Digital India. Educated India.
Right. So, these are the two interesting properties that are associated with Hermitian matrices. First is that the eigenvalues are real, and second is the eigenvectors that you get are mutually orthogonal. I think we had discussed this, right, we had worked this out. Okay. So, if you are a little rusty on this, just flip back and go to I think that know thy matrices, lecture 5. We must have discussed this in lecture 5. No, 6b, eigenvalues, right, 6b. Okay. So, let me now, knowing all this, write down your familiar eigenvalue equation, matrix eigenvalue equation in that expanded form that we had worked out. I hope you are not completely at a loss when I write this. What is matrix eigenvalue equation? Hx equal to lambda x, right, and what we saw was that there is going to be n number of eigenvectors, correspondingly there is going to be an eigenvalue, right, and then what we did is these vectors are what they are column matrices. We said why not combine all the columns and make one square matrix, remember, and then we had constructed a square matrix like this. So, what I show here instead of writing a x11 and all that is each of these columns is an eigenvector. Okay. Each column is an eigenvector. Okay. Now, do you remember this equation? We had written H matrix multiplied by capital X matrix equal to capital X multiplied by lambda. What is lambda matrix? Does this ring a bell? Remember this equation? Fine. Now see, what would be the adjoint of this X matrix? Columns become rows and you have to take complex conjugates. So, is everybody okay if I write it like this, right? Now, since everybody is okay with this, will you agree with me when I say that this adjoint is also the inverse of the same matrix? Work it out. It is convenient if you multiply this matrix by the adjoint. Okay, let this be on the left, let this be on the right. So, what is the 1 1 element? This one, what is this color? Blue. So, this is blue row complex multiplied by blue column. What should it be? It should be 1. Do not say blue, it should be 1. Yeah. Orthogonal eigenvectors, right? Mutually orthogonal eigenvectors, orthonormal eigenvectors actually. This should be 1. Now, the problem comes when you want to see what is 1 2. What will be the 1 2 element? Blue star multiplied by what color is this? Green. I will believe you. So, what should it be? If they are orthogonal, you are multiplying the elements and adding them up, you should get 0. So, off diagonal elements are all going to be 0. Okay, what about 2 2? Green star multiplied by green, that is also 1. Okay, what about the last one? What is this color? That is white. So white star multiplied by white, that is 1. So all the diagonal elements become 1, all off diagonal elements become 0. So the adjoint here is the inverse. Okay. So if the adjoint is the inverse, which matrix am I talking about? I am talking about, yeah, of course it's unitary. I am talking about the matrix of eigenvectors, right? So as Rahul has said correctly, the matrix of eigenvectors thus turns out to be unitary. Right? Had we discussed this earlier? I don't think so. We have? Okay. So this is unitary. Right. So now what I can do is, next part I definitely remember we discussed earlier. If I now left multiply the left hand side by the adjoint, yes. Then on the left hand side what do I have? I have a similarity transformation. On the right hand side what will happen? You multiply the matrix of eigenvectors by its adjoint, which is also the inverse, you get unit matrix, right? So this is the equation, right? And if we now shed the tomfoolery of colored columns and colored rows and all that, we can write down the equation like this: A equal to U inverse H U. I think earlier we had written, not A, sorry, lambda equal to U inverse H U. Earlier I think we had written lambda equal to X inverse H X, right. Here I want to write U to stress the fact that it is unitary, number 1. Number 2, to be at least somewhat be in line with Bishop's notation. Okay. So if I read this and if I try to speak this, say this in English, what will I say? The lambda matrix is obtained by a unitary transformation of the Hermitian matrix, right. The matrix which has the eigenvalues of the Hermitian matrix along the diagonal and 0 everywhere else is obtained by a unitary transformation of the Hermitian matrix. Okay. But while we say this, please do not forget that this is not just any unitary matrix, it is a particular unitary matrix. Which matrix is that? It is a matrix of the eigenvectors. Okay. So far so good. Any question? If not, let us clean this up a little bit. This is what we will need, right. H is a Hermitian matrix. Better write this down, because the thing is, at one point we are going to erase this also. There is only so much you can write on a slide, right, but we will need this, and it is very easy to forget what we are saying now in the maze that we get into after this. So please write down that H equal to sum over R dr multiplied by dr adjoint, that is one, and second is lambda equal to U inverse H U. We are going to need this later on. Of course, you are all masters of manipulation, you know how to take square of whole sides, then transpose and take cube root and get the answer. That is basically what we are trying to do after this. Please write this. Okay. Can we go ahead now? Lambda equal to U inverse H U. Okay. So now let us now talk about two equivalent matrices, dr and d prime r. Dr is any transformation matrix that you get. You have used some basis without bothering about whether they are orthonormal or not, right. You have used some basis and you have got the transformation matrices. Using the transformation matrices, you have built the representation. So dr is that kind of a transformation matrix, right. Dr is a transformation, an innocent transformation matrix. We do not bother about what the basis is. We have just used some basis that we like and we have got dr, we know nothing more, alright. D prime r is a little less innocent, because d prime r is obtained by the similarity transformation of dr, right. Of course, anybody can call my bluff at this point and say that dr is also it is also possible to get dr by a unitary by a similarity transformation of d prime r. That is right, but what we are saying is that we start with dr, perform a similarity transformation and get d prime r. And if you notice, we are performing the similarity transformation with a particular unitary matrix. Which matrix is that? It is the matrix of the eigenvalues of H. Eigenvectors, not eigenvalues, sorry. It is the matrix of eigenvectors of the H matrix. Okay. What is H matrix? This is how you get H matrix. So, see, everything is correlated. Okay, please, it's important to understand here that we are not really taking arbitrary matrices and multiplying left, right and center. Okay. You start with dr, all right. If you perform a similarity transformation, you are going to get d prime r. On the other hand, if you take all the drs and their adjoints, multiply and sum over all the symmetry operations, then you generate a matrix H. From that, you can get the matrix of eigenvectors U. D prime R is the similarity transform of dr using this matrix of eigenvectors. Okay. So, there is a correlation. It is not as if D prime H are all uncorrelated scattered, no, everything is correlated, alright. We will come back to this, but this also please take down lest we forget later on. D prime R equal to U inverse dr U. Okay. So, our basic first matrix is dr. Will you believe me if I write this? The adjoint of d prime r is the similarity transformation of the adjoint of dr. Yes.
U is the matrix of eigenvectors of
H.
Is U diagonal matrix?
U cannot be diagonal matrix, right? Lambda is diagonal matrix. I mean, I should not say that it cannot be diagonal matrix, but in the most general case it isn't, it is not, alright. So, adjoint of d prime r is also a similar similarity transformation of the adjoint of dr. Okay, so far so good. Now, with this what we do is we can start playing. What do? I know what H is. H is sum over R dr dagger. So, what I can do is I can take this definition and substitute there, right. This is what it is. So, I might as well expand H in the definition of lambda. Okay, you see where we are going. You are going a long way, but the destination is interesting. So, this is what we write, lambda equal to sum over R U inverse dr dagger U. What can we do next? What should I do next? Replace by what? By which equation? Well, eventually we will do that also, but then see the second equation relates dr dagger with d prime r dagger. Okay. What we can try to do is this, we have to get to d prime r of course. So, we need to convert this into a product of similarity transformations. So, here you see dr is left multiplied by u inverse, dr dagger is right multiplied by u. So, you can put in E, and E can be obtained in many different ways. So, this time we choose to obtain E by writing u inverse, right. U inverse. So, if this was u and this was u inverse, we would have written it as u inverse u, no problem. Okay. So, when I write that, what do I get? U inverse dr u inverse dr dagger U, right. The first one is a similarity transformation. What does it give me? It gives me d prime r, d prime r. Second one is also a similarity transformation, d prime r dagger. Okay. So nice. I can write this, and what I can do is, if I sum this up over r, then I get lambda, right. So here what we did is that we just wrote the terms. Now if you sum it over r, then you get lambda once again. Okay. What do I do next? Let me see what a diagonal element is to start with. You remember lambda is a diagonal matrix, right? See, this is what the diagonal element is going to be. Lambda jj will be once again sum over r, sum over j, d ij prime r multiplied by d ji prime r dagger. Is that correct? Let us see what is lambda 1 1. Lambda 1 1. What is lambda 1 1? d 1 1 prime r multiplied by d 1 1 prime r dagger plus d 1 2 prime r or d 2 1 prime r? d 1 2 prime r, right. So the summation is on j, the second one, d 1 2 prime r multiplied by d 2 1 prime a dagger. Summation is on j, so j is the first element here, and so on and so forth. You sum j equal to 1 to n. Is that, are we all comfortable with this? It's a diagonal element. I don't care about off diagonal elements, because I know already that diagonal element off diagonal elements are all 0, right. I only care about the diagonal elements. What are the diagonal elements? Are they all 1? Then what are they? The lambda values, right, the eigen values. So what are the eigen values? They are all real, right? Why? Hermitian. Hermitian. Are they all positive? I don't know. Maybe, may not be. Probability is 50%, since we don't know anything else. Okay, but they are real numbers, that much is sure. Okay. So are we all okay with this notation? Sum over j, dji prime r multiplied by dji prime r dagger. Okay with this? The advantage of that is that I write this here. What is the first one? The first element is dij prime r, second one is dij prime r star, right. So you are multiplying complex conjugates. If I multiply complex conjugates, then what should I get? As you said, we should get the mod value, right? We should get the positive value. We cannot get negative value. So the point is, lambda ii has to be a real and positive element. You are right. It's just that we have to prove it. Fine. Now what do I do? How does it help if it is real and positive? What are the things that we can do with real and positive numbers that we cannot do with real and negative numbers? We can happily take square root without having to bother about this annoying I coming in, right? That is what we are going to do. Okay. So this is lambda. This is the lambda matrix, right? Lambda 1 1, lambda 2 2, etc. up to lambda n. These are the non-zero elements, and as we have seen, these are all positive quantities, positive and real quantities. All of diagonal elements are 0. So see, what is this? This is dji r dagger. What is the meaning of dagger? I transpose and I take complex conjugate. Okay. So now see ijth, what is this, jith element of the transpose is the ijth element of the original matrix, right. So that is what I have written, right. Instead of, if I write ij, then I can lose the transpose sign, but I still have to have star because it's adjoint, not transpose. Dagger means adjoint, right. So you transpose as well as write the complex conjugate. Okay. So now what I am doing is that I am kind of transposing back, but keeping the complex conjugates. And the advantage is that now you are multiplying each number by its own complex conjugate. So you know what the sum is going to be. The sum is going to be a real positive quantity, right. Okay. Right. So this is lambda. Now since all these lambda I values are real and positive, I can happily take square root. Of course you might ask, why would I want to take square root in the first place? Two things. First is that it's a hint. Secondly, I have the benefit of hindsight. What is lambda to the power half? How would I define lambda to the power half? Lambda to the power half multiplied by lambda to the power half equal to lambda. Okay. So what is lambda to the power half? What will the matrix be? What will be the matrix elements? What is the 1 1 element of lambda to the power half? Lambda 1 1 to the power half. What is the 2 2 element? Lambda 2 2 to the power half. Is as simple as that. Okay. But now that we have written this matrix, are you convinced that it is actually lambda to the power half? Multiply it with yourself, don't you get back lambda? Right. So no issue with that. What is lambda to the power minus half? Just change half to minus half, nothing else. Trivial, but it's going to come handy. Okay. So will you agree with me if I say that the adjoint of lambda to the power half is also lambda to the power half? It's very obvious, diagonal matrix, no issue. Similarly, the adjoint of lambda to the power minus half is equal to lambda to the power minus half, right. So now let us write it like this. Let us say d double prime r is lambda to the power minus half d prime r lambda to the power half. You agree with this? The same thing holds for the adjoints, right. So now we are going to prove that these matrices, the double prime matrices, are unitary, right. That is the final goal, yeah. But let us work with this now. So see, R is a general operation, right. Let us focus on one operation, S. What is d double prime S adjoint? What is that? Lambda to the power minus half d prime r lambda to the power half, then lambda to the power half d prime s dagger, it is correct. So we will go back to the earlier one, lambda to the power minus half. See, earlier one does not matter, right, because when we do that manipulation, instead of writing u inverse, you have to write u inverse u and it gets solved. No? Okay. Okay. I think it works out, we will see, but let us finish this first. Okay. So, this is fine. What is the next step? What is the next step here? Yes. What is lambda? U inverse HU, right? So, I can write it like this, lambda to the power minus half d prime s U inverse HU, then adjoint of d prime s lambda to the power minus half. What do we do next? What can I do next? H. What is H? Sum over R dr dagger. You can put that in, and this is what we get, lambda to the power minus half d prime s U inverse sum over R dr dagger U d prime s dagger lambda to the power minus half. What do we do next? Without losing any generality, I can bring the U inverse inside, right? Because what are we summing over? We are summing over all R. Is U defined, is U different for every R? No. Where did we get U from? What is U? It is the matrix of the eigenvectors of H. How did we get H? What is H? Sum over R dr dagger, right? So, it does not matter which symmetry operation you are working with, okay, it is the same. So, I bring U inverse inside, and this is what I get. What do I do now? Yes. What is U inverse dru? That is d prime R, and this is d prime R dagger. That is what we had said, right? So, that is the contradiction. Okay. All right. I will have to work on this, but let us go ahead with this. Fine. So, again let us bring d prime s in, and this is what we get, lambda to the power minus half sum over R d prime s d prime R dagger d prime s dagger lambda to the power minus half. What do I do next? So, this is what it is. What do I do next? Yes. So, after all, we are talking about a product, right? I have d prime s multiplied by d prime R dagger multiplied by d prime s dagger. What is R? What is S? They are symmetry operations. S is a particular symmetry operation, R is a general notation. So, we can have different symmetry operations substituting for R, right. So, let us say that SR equal to T. So, is T a variable or a constant? T is a variable, right, because R is a variable. So, if SR equal to T, then this is going to be d prime T and this is going to be d prime T adjoint. What is d prime T? U inverse dt U as we have defined it, right. This is U inverse adjoint of dt U as we have defined it. So, this is what d double prime S dagger is. What do I do now? Earlier we had put in U inverse. Now we can eliminate, right? And this is what you get. What do I do next? I can bring U inverse out, so I am kind of going in a reverse direction now, right? So this is what I have. D double prime S adjoint equal to lambda to the power minus half U inverse sum over T dt dagger U lambda to the power minus half. What is this? This is H, right? Why is this H? I thought H is sum over R. What do you have? Lambda to the power minus half U inverse H U lambda to the power minus half. What is this? So what is lambda to the power minus half lambda to the power minus half? E. So D double prime S is unitary, because D double prime S multiplied by its own adjoint gives you E, right? So of course, and it's what we really want to know after all this is that how do I generate a unitary representation? What is the recipe? That is something that is going to come handy. So recipe is this: you choose whatever basis you want to work with, and for that basis you work out the transformation matrices for all the symmetry operations in the point group. So they are going to be dr, right? Now then you find the adjoints for every matrix, that is dr dagger. Next, work out the Hermitian matrix, sum over R dr dagger. Doable? Next, what we need to do is, when we need to work out the eigenvalues first, right? We have done this earlier with an example of a matrix. We worked out the eigenvalues first. How did we work out the eigenvalues? By solving the characteristic equation. What is the characteristic equation? Yes? Yes, they are equal to 0. So when you solve that, you get all the values of lambda. I mean, you get lambda 1 1, lambda 2 2, and so on and so forth. You construct the matrix lambda. If you know what lambda is, you can construct what is lambda. You can construct lambda to the power half, lambda to the power minus half. Next, you can work out U, which is the matrix of eigenvectors. Once again, this is something that we did a few weeks earlier. Not for a Hermitian matrix maybe, but for some matrix. And then once you have got U, well, you can work out the D prime R matrices by performing the similarity transformation. And finally, since you know lambda already, you work out the unitary matrices by performing the second similarity transformation on the D prime R. So now, irrespective of what basis that I have started with, I can convert all the matrices to unitary matrices and thereby generate a unitary representation. Okay? So that is something that we should be able to do.